So, good morning, everyone. Today we come into the last segment of our this chapter, this transform chapters, basically. So, till now, over here we have discussed about Fourier series, Fourier transform, discrete Fourier series, discrete Fourier transform. Then we have also discussed about DFT and how using the FFT we can implement the DFT that we have also seen. So if you look over here in the transforms Fourier series and Fourier transforms, they were mainly meant for the continuous time signal, whereas discrete Fourier series, discrete time Fourier transform and discrete Fourier transform, they were meant for discrete time signals and systems. Okay. Now, in general, the signals that are present which can be analyzed using all these transforms which we have discussed till date, they are either energy signals or power signals. Okay. However, all these transforms, they are not capable to analyze the neither energy nor power signals. Okay. So we have looked into that there is a category of signals which is neither a power signal or neither a energy signal, nor a energy signal. Okay, so neither a power signal nor an energy signal, right? So, what about this things? How to analyze this kind of signals? Okay, so before going into the depth, let's look into the evolution of these transforms from the beginning. I have already discussed, but let us again discuss. Okay. So, when we talk about Fourier series, we discuss that it can only analyze periodic signals. Okay. Then, from the Fourier series, with certain assumptions, we got Fourier transform. Okay. In the Fourier transform, what we found is that we can analyze both powers, these periodic signals and non-periodic signals. Okay. So you can see there is a transformation from Fourier series to Fourier transform with certain assumptions, right? And by assuming certain things, we were able to enlarge the capability of the Fourier series. Okay. So by the generalization, we got Fourier transform, and it was a better transform as compared to the Fourier series, as it was able to analyze a large number of signals. Now the thing is that this Fourier transform, it is a robust transform, and it can be used in many applications. Okay, say for example in medical applications you can definitely use it. You can use it in power electronics, you can use it in normal digital signal processing, you can use it in say geology for analyzing the seismic activity, and whatever the field you name, whatever the technical study you can name, over there the Fourier transform has played an important role. Okay. So it is a very robust transform, right? Now it has also got some limitations. What are the limitations? I already told you a few moments back. Fourier transform, it is only able to analyze energy signals and power signals. It is not able to handle the neither energy nor power signals. Okay. So over here again, if we do certain mathematical manipulations, then we can get into the Laplace transform domain. Okay, and by doing this, what we are doing, we are again generalizing the Fourier transform into a more generalized transform, which is regarded as Laplace transform. Okay, so we started with basically see Fourier series, then we generalized it to get the Fourier transform. Now Fourier transform is nothing but, if it further generalize it, we will get Laplace transform, and this Laplace transform, it will be capable to analyze not only the energy signals but also the power signals and neither energy nor power signals. Okay, so this is the power of Laplace transform. Okay, so why this happens? If you look into the Fourier series, we were mostly into this sinusoidal waves. Okay, when we talked about the Fourier transform, we were basically in the complex domain only. Okay, there was no real component to the system. Okay, so when, so frequency in Fourier transform, if you remember, it is associated with the component J. So what is J? J is nothing but a complex number, right? So that's why it is called that Fourier transform. It is basically present or restricted in the complex domain. Now that complex domain, it is basically a single axis. When we generalize the Fourier transform to Laplace transform, we basically get into a 2D plane where the x-axis is the real axis and y-axis is imaginary axis. Okay, or complex domain. So this y-axis, it is the frequency axis, what we were dealing in the Fourier transform. Okay, in Fourier transform, when we perform the Fourier transform, suppose we are having a signal which is having a time scale and amplitude. If we perform Fourier transform, what we get? Frequency versus amplitude. So from time domain, we were shifting to the frequency domain. Okay, so in Laplace transform, if I say where is the Fourier transform restricted to, the Fourier transform is restricted only to the y-axis, which is the complex domain. Okay, so by allowing this sigma, this real component into the Laplace domain, we will later on see in a few moments. What we are doing is that we are allowing the transform to handle even the signals which could not be handled using the Fourier transform. Okay, so when we come over here, so this when we talk about this Laplace transform, it is basically um, dealt. It is basically dealing with the continuous time signals and systems. Okay, but our main aim is to discuss about the biomedical signal processing, and when we talk about that, we basically mean that digital signal processing, how it can be applied to the medical signals, or you can, in other words, you can say application of digital signal processing in medicine. So that is our course name, biomedical signal processing. So it is basically a combination of two different fields, medicine and the digital signal processing. Okay, so by combining these two, we get this thing. So when we talk about this Laplace transform, as I already told you, what is happening, we are dealing with continuous time signals. That means we will be having analog frequency over here. Then we will be discussing about the digital signal processing systems. Over there, we will be having digital frequency. So basically, we will be discussing about two types of frequency. If you see on my right, analog frequency, this is given by this ohm sign. So this is basically also called the omega. So this omega, which is having the ohm sign, it is related to the, or it is used to represent the analog frequency. And the other omega, which is similar to the w, it is used to represent the digital frequency. It is used to represent the digital frequency. So if you see in the first case, xt, if you apply Fourier transform or the inverse Fourier transform, we have used this omega sign. And when we are talking with xn, and if you are applying dtft or dft, if you are applying the dtft, then you are having this analog frequency. We have already discussed why that is so, right? And in if you are using DFT, it will be x of omega, okay, and vice versa. So when we are talking about this, we have just seen that Laplace transform, it is mainly meant for the continuous time signals and system. So how will we analyze the other signal processing systems which are working in the digital domain? So in that case, we need to have another transform which is regarded as the Z transform, okay, which is regarded as the Z transform, okay. Now the Laplace transform, it is meant for the continuous time signals and systems, for the analysis of the continuous time signals and systems, whereas the Z transform, it is meant to analyze the discrete time signals and systems. And digital systems, they are nothing but discrete time systems. So we need to study both this Laplace transform and Z transform. Now, when I say that we need to study both Laplace transform and Z transform, why this is so? This is because when this signal processing domain, these were being developed, initially the Laplace transform was developed. Why? Because at that time, mostly the signal processing meant analog signal processing using the circuits. Okay, so all of them were continuous time signals or systems, whatever the signals and systems you are getting. Okay, now when those systems were developed, so if you want to develop another system of that one, if suppose it is working fine in the continuous time domain. So when you try to design any digital system, you may be interested in emulating the analog system into a digital system. Okay, why that is so? Because that is tested, okay, and it has been verified that it works fine. So that system configuration, it is expected that it will also work in the digital domain, okay. So but we are now having two things. One is the analog frequency, second is the digital frequency. Because I am talking about two systems, I am emulating the continuous time systems into digital systems, right? So what happens is that, as I told you, like that one, so this Laplace transform, it can help us in identifying the criteria for developing stable system. Okay, it can help us in identifying the criteria for developing the stable digital systems, right? Now if this is the case, then our life will be much easier, and that is what the first instances of digital filter systems they were considering. Okay, so they took analog systems, they took the characteristics of that one, they applied some transform to get into the Z transform. Okay, so there has to be some connection between the Laplace transform and Z transform, otherwise how will you apply that transformation? It is not possible, right? So that is why before getting into the digital signal processing systems, we need to understand the properties of the Laplace transform and the properties of the Z transform. I will not be, it is not a BTech UG level class. So just I will be giving you the basic requirements, what is needed for this class. Okay. So there are many other properties which if you want you can go and study. So we'll be understanding in today's class what is the relationship between the Laplace transform and how it is related to the Z transform after understanding both Laplace transform and Z transform. Okay. Another important thing, if you see the Laplace transforms, since they are continuous time signals, they are being represented with the signals of systems, they are being represented with the differential equations. If you find that there are some differential equations in any system, you can blindly say that we need to apply Laplace transform. Whereas uh, so if you see, it will be just like this, dy by dx or d2y by dx2, like that. So it will be a component of dy by dx in this form. Okay. On the other hand, the same dy by dx, it can also be represented in this fashion if it is a discrete time signal, and this type of representation it is regarded as difference equation. Okay, this type of representation it is regarded as difference equation. So if when we will be talking about representing digital signals and systems, we will be having, we will be using the difference equations, whereas if we will be discussing about the Laplace transform, then we will be using the differential equations. Now let's come to this this Fourier transform to Laplace transform, how it happens, because it is very important to understand. As I told you, Fourier transform, it is restricted in the complex domain, and hence it can only be analyzing, it will be able to analyze the restricted class of signals. Okay. If there are any signals which are exponentially growing, say like this, or the ramp function which we studied in our one of our previous classes, in those cases the Fourier transform it fails. It is, Fourier transform is not able to analyze unstable or even marginally stable systems. Okay. So as I told you, why? Because Fourier transform it is mainly restricted in the complex plane s equals to j omega. Okay. Now this problem it can be solved if we convert this j omega to s. Now what is s? S is equal to sigma plus j omega. So basically, if you remember, in Fourier transform we had the operator e to the power j omega. However, if we replace this j omega with e to the power st, then the transform what we get, it is called bilateral Laplace transform. Okay. Now let us see what we meant. So suppose we want to go to the frequency domain. So if we apply the Fourier transform on the signal x of t, we get the Fourier transform integral of minus infinity to infinity x of t e to the power minus j omega t dt. Okay. Now the inverse Fourier transform, it is given by xt equals to f inverse of x of j omega equals to 1 by 2 pi integral of minus infinity to infinity capital X of j omega e to the power j omega t d omega. Right. So this was the Fourier transform and this was the inverse Fourier transform. Right. Now as I told, when there is an exponentially growing signal, that means it is growing, so it will not come within the bounds as time tending to infinity. So what we can do over there? The thing is that we can multiply the signal with e to the power minus sigma t. And when we do that, how does this look like? This would look like something like this, time amplitude, right? So it will be a decaying function. So at time tending to infinity, your amplitude will be tending to 0. That means even if you multiply this with your exponentially increasing function or the ramp function at time tending to 0, the amplitude will be tending to 0, right? So this is the trick, and that's why, as I told you, the Laplace transform, we are having both sigma and j omega. Okay, because there is a real component and there is an imaginary component, and our Fourier transform, it only existed on the y-axis, which is the complex axis. And since we are multiplying the signal with e to the power minus sigma t, this sigma, which is the real axis, we are getting this. You are getting my point? Now, due to this reason, what is happening? Let's see. F of x of t multiplied by e to the power sigma t is equal to integral of minus infinity to infinity x of t e to the power minus sigma t. This is the signal. Basically, we have changed the signal x of t to this thing. So see, we have just replaced it, right? We have just replaced it. If you compare these two with this, because we have changed the signal, right? Now, if you just rearrange this thing, x of t equals to e to the power minus sigma plus j omega t dt. Okay, so we will consider this as capital X of sigma plus j omega. Similarly, when we talk about the inverse Fourier transform, we will get x of t, it will be replaced with xt multiplied by e to the power minus sigma t equals to 1 by 2 pi integral of minus infinity to infinity sigma plus j omega multiplied by e to the power, because this is the sigma plus j omega multiplied by e to the power j omega t d omega, like this one. But if you look over here, what is happening? This d omega, it is associated with the Fourier transform. Okay, it is associated with the Fourier transform. Now, or we can say e to the power j omega, it is the Laplace this Fourier transform operator. Okay, but what we have used, we have got a new operator sigma plus j omega, which is represented by the letter s, and this s is regarded as the Laplace operator. Okay, which is regarded as the Laplace operator. And if you do the differentiation over here, so you get d omega equals to 1 by j ds. And if you go back, if you look over here in the Laplace transform, there is no such issue. You can just directly change the s and put it over here. However, in the inverse Laplace transform, if you say d omega is equal to 1 by j ds, so d omega has been replaced and this extra j, it has been put in. You're getting my point? So if you see, this is what, if you compare this equation and the next page equation, there is only a j addition and this d omega, it has been changed to ds. Okay, so see, just by introducing a small trick, we were able to generalize the Fourier transform, or as he said, we were able to maximize the potential of the Fourier transform. And this maximization in the new transform, what we got is regarded as the this maximized transformation, it is regarded as the Laplace transform. Now, just like in the this Fourier transforms, discrete Fourier transform, and all these things, we had this convolution integral. Over here also you will be having convolution integral. Similar process, so I am not discussing over here. So x of t equal, if you give an input to the h of t, you get y of t, which is equal to xt convolution of h of t. It's just like the similar thing. Otherwise, also if you want to do it in the frequency domain, you perform the Laplace transform, go to the x's, h's, then ys would be x's multiplied by h's, and you perform the inverse Laplace transform, you get y. Okay. Now coming to the Z transform, it is very important. As I already told you few moments back, Z transform is used to solve difference equations for discrete time signals, right? And it is also a counterpart for the continuous time signals. This is very important. Solves difference equations for discrete time signals, and it is a counterpart for the continuous time signals. So continuous time signals are represented by differential equations, whereas the difference equations represent DT signals, all the same thing. So in this case, the output of any given system, it is given by yn equals to hz z to the power n. Okay, hz z to the power n. Okay, and what is this hz? Hz is nothing but your impulse response in the z plane, and it is given by h of z equals to summation of n equals to minus infinity to infinity h of n, which is the impulse response in the time domain, multiplied by z to the power minus n. Okay, z to the power minus n. So if we want to generalize this equation, so the z transform, it is given by x of z equals to summation of n equals to minus infinity to infinity x of n into z to the power minus n. Okay. So suppose I am given with a number or a signal xn equals to 1, 2, 3, 4, say for example. Okay. So if I ask you to find out the z transform, what will be the z transform? So x of z, it should be equals to 1 into z to the power minus 0 plus 2 into z to the power minus 1 plus 3 into z to the power minus 2 plus 4 into z to the power minus 3. So what is n? N equals to यहाँ पे 0, 1, 2, 3. So xn value, or what is the corresponding n value? You just put z to the power minus that n value. So it is as simple as that. If you want to convert any signal, real signal, and if you want to convert it into a complex domain signal, then you can convert it in a very simplistic manner. And this generalized equation, where the time domain, it varies from minus infinity to infinity, it is regarded as the bilateral Z transform of Xn. We have also seen that in the Laplace domain, bilateral Laplace transform. Now the thing is that biomedical signals and systems, they are mainly causal systems. They are mainly causal systems. Now, since they are causal systems, this n, it is restricted in the region of 0 to infinity. It is restricted in the region of 0 to infinity, and this modified equation, it is regarded as unilateral Z transform. Okay. So in this equation, what does this indicate? It indicates xn is equal to 0 for all values of n less than 0. What was the condition of the causal signals? Causal signals, it started from 0 and it was a right-handed signal. Okay. So lastly, as I told you, x1z is useful to calculate the response of a causal system to a causal input. Now the most intriguing part, which I was telling you from the beginning, that we need to understand what is the relationship between the Z transform and the Laplace transform. Okay. So if you look over here, I have written one term x cap. What is this x cap? X cap is nothing but the sampled xn signal, sampled xt signal. Okay, sampled xt signal. Now, if we take the Laplace transform at both the end, this equation it converts into capital X of s, which is equal to summation of n equals to minus infinity to infinity x of nt into e to the power minus nst. Okay. How few moments back we have seen that z transform is given by xz equals to summation of minus n equals to minus infinity to infinity x of n z to the power minus n. If you see this part is equal, right? So there are some similarities over here. And what is the similarity? So both the equations they will become similar if z is equal to e to the power st. Okay. So we know that s is equal to sigma plus j omega. So we can put z equals to it was sigma plus j omega multiplied by t, and you then open this bracket. So after doing this, if you find out modulus of z, it is equal to e to the power sigma t, and we have a phase angle of omega t. We have a phase angle of omega t, right? क्या नींद आ रहा है? शक्ल तो वैसे ही लग रहा है. हाँ हाँ. So what happens over here is that if you look, when sigma is equal to 0, modulus of z it would become 1. It is an equation of circle. Okay, e to the power j ये अगर ये करोगे z equals to e to the power j omega t, it is cos omega t plus j sin omega t. What is it? Nothing but ये equation of a circle. Okay. So I have already discussed about this one. This is the Laplace domain, which is also regarded as the S-plane, right? Now, when we go into the Z-plane, we have two things. One is real Z and imaginary Z. Okay, real Z and imaginary Z. Now, when we will be mapping the S-plane into the Z-plane, we need to look into the characteristics. Okay. So when we say when sigma is 0, where is sigma 0 in the S-plane? At this frequency axis. Okay. So when the sigma is 0, we get a value of 1, and we know that it is an equation for an unit circle. Unit circle means a circle having a radius of 1. So we get a circle, its radius is 1. Okay. Now the interesting thing is, where is the frequency? Because over here in the S-plane our frequency was the y-axis. Now in the next case, where is the frequency? Is it the real Z? Is it the imaginary Z? So where is the frequency component gone? The answer lies in the mapping itself. this straight line has been converted into a circle. So this circle is the frequency axis. This circle is the frequency axis when the radius is equal to 1. Okay, when the radius is equal to 1, the circle is frequency axis. Okay, when sigma is less than 0, that means we are on the left hand side of the plane of S plane. What will happen? Minus sigma ये t, when it is less than ये 1, कहाँ पे जाएगा? It is less than 0. Oh, sorry, it is less than 0. So what will happen? Uh, it will be in the inside the circle. Okay. Similarly, if when sigma is greater than 0, it is outside the circle. Okay. So this is the mapping of the from the Laplace transform to the Z transform. Okay. It is the mapping from the Laplace transform to the Z transform. Now there is a problem over here. What is the problem? If you look into the frequency axis of S plane, it varies from minus infinity to infinity, plus infinity. Minus infinity to plus infinity. But when we are talking about that frequency is limited to the circle, so what will be having? It will start at 0, it will come to pi, it will again come to 2 pi, and 0 and 2 pi are same at the same location. Okay. So what? So we are having 0 to, if you plot the frequency axis, we will be having 0, pi, 2 pi. But if you further move over here, 2 pi के बाद अगर फिर यहाँ पे आना चाहते हो 3 pi, 4 pi. But this 3 pi is nothing but ये pi. 2 pi is nothing but 4 pi. Similarly, if you go back into the negative here, you will get minus pi, minus 2 pi. So again इसको आप ये कर रहे हो, both are same here. So pi will also be minus pi also. 2 pi is again minus 2 pi. Okay. So see, when we have converted into the Z plane, we are only restricted in this location 0 to 2 pi. We cannot go beyond that. And whatever the other frequency components are there, they will be superimposed onto the same locations. So it is a one to many to one transformation, because many points in the S plane, they will be transformed into a single point on the Z plane. Okay, many to one frequency transformation. Understood? Because see, this is the basics of digital filtering, and from next class onwards we will be getting into the digital filtering. So if you are not understanding, please get it clear. Okay. Due to this reason, what is happening? There is a many to one transformation. Okay, there is a many to one transformation. Okay, so you have to take care of this thing. Okay. Another important thing is that I will just go back over here. If you see, when I said I have sampled the signal, in the constituent signal, in the constituent signals, See, there are two signal components. One is the original signal and the other one is the impulse train. Impulse train, it is having its own frequency, right? So the frequency of the impulse train, it is called the sampling frequency. It is regarded as sampling frequency and it is given by Fs. Okay. At what frequency you will be getting the samples. Okay. On the other hand, you will be having x of nt, or you can say the normal signal. It will be having its own signal components. Okay. So here we have f of m, maximum frequency of the signal and the sampling frequency. Okay, these are two important frequency components which we need to deal with when we are dealing with any digital signal. Okay, now coming over here again to the z plane, we are having 0 and 2 pi. 2 pi is the maximum frequency. Okay, so there is a criteria which is regarded as Nyquist criteria, and the Nyquist criteria says the sampling frequency, it should be greater than equal to 2 of fm, where fs equal to 2 of fm is the lower critical limit. Okay, the larger the fs, better will be the uh, signal what do you call reconstruction. Okay, so the lower critical limit is fs equals to 2 of fm. Okay, so we can clearly see over here fs should be greater than fm. Okay, so herein what is the greatest frequency we have? Greatest frequency is 2 pi. So at this position we should have f of s. At this position we should have f of s. Sampling frequency is always put at 2 pi. Okay, and at the lower critical limit 2 of fm. So fm कहाँ पे होगा? fm equals to fs by 2, which is the lower critical limit. So where should be the fm in the lower critical limit? It should be at pi, because it is at 2 pi, your fm is at pi. Okay, now the thing is that again is 0 to pi, 2 pi. So suppose we are having a frequency component like this. In our last one of the classes, I talked about I gave you the chart of the discrete Fourier transform, right? Now over there, if you see, when we are sampling the signal, the frequency was getting repeated, right? The frequency was getting repeated. So 0 to 2 pi, frequency will again repeat itself in pi to 2 pi. Similarly, it will also being done in the negative half also. So 0 to minus pi, again minus pi to minus 2 pi, and so on. Okay, but we will be restricting ourselves to 0 to 2 pi. Now if this is the case, when you are having that 0 to pi and pi to 2 pi, at this position we are having a very good separation. But when we talk about this digital this what do you call it? Analog to digital converters, which convert analog signal to digital converters, and if you are working with low cost signals, then there would be some spectral leakage. Okay, because they are not ideal components. Mostly whatever the components we use, they are not ideal components. So in the low cost one, the idleness will be much far away. Okay. So in those conditions, what happens is that there would be some spectral leakage, and there would be mixing up of these frequency components, and this is regarded as the aliasing. When high frequency components are getting mixed up with the low frequency components when it is repeating, so at this point there would be mixing up of high frequency component of the original signal with the low frequency component of the repeating signal. Then the thing is called aliasing. And once aliasing happens, you cannot, your signal is totally corrupted, you cannot use it. Okay. So even though theoretically it is told that your fs should be equals to 2 of fm, however, if you increase the fs, it is, it would be better for you, as it will help you in eliminating any chances of signal corruption. Okay. However, in that case, what will happen? Say for example, if you do f dash fs dash, okay. Say for example, initially you are having fs of 200. Okay. Now what you did, your fm sorry, your fm would be 100 hertz. Now you have increased the sampling frequency to say 300. Now this point and this point is fixed. You have fixed now this 2 pi as the 300. So over here it will be 150. You sure? So since it would be 150, where would be your previously this maximum frequency of your signal? It would have, if it is 150, that means it would have shifted somewhere over here. I am not going into the actual mathematics. So somewhere over here. So what is the problem? The problem is that when you are going from, initially you had 0 to pi full spectrum. Now the same spectrum 0 to 100, it is being compressed into a smaller region. So you will be losing the resolution. You will be losing the resolution. समझे? How will you lose the resolution? The thing is that now there are less number of students in each of the days. Two people you are sitting. So if I have to identify, I will be identify it very clearly. However, if there are lot number many of students, and in one desk I put three students, will you be comfortable? Why? Because in between the space is very less. Okay, and since the space is very less, what is happening? Within a particular space, the number of points has increased. So it has been quizzed. Now, say for this, that you further increase the number of the students. If I ask some more students to sit in, you will become much more uncomfortable, because within the same space, lot number students have to be accommodated. So in this way, what is happening? You are compressing the, within the same space, we are compressing a large number of frequency components. Okay. So from moving one point to other point, it will be very difficult. And if you want to design, since they are very close, if I have to pick up one student, it will become very difficult. Okay. So it will increase the difficulty. So what is this called? This is called the cramping of the frequency component, or you can say that they get compressed within the frequency component. The frequencies, they are getting compressed. Okay. Now when this compression happens, as I told you, designing of the filters, it becomes very difficult. Okay, this is one problem. Another problem is that you are sampling at say 300 hertz more, so 100 data points per second will be higher, more. 200 hertz when you will be having in 1 second 200 data points to accommodate you. So somewhere you have to trade off. Okay, somewhere you have to trade off. So you have to look into the thing that you do not have the aliasing, and also you have to keep in mind that you do not want to oversample beyond a certain limit, such that what happens is that your uh, uh, such that there is no yeah, cramping of the signal, and you can design the filters in a more comfortable manner. Okay, so this is it. And also your storage, what will be required, it will be quite less. Okay. Now next is relationship between Fourier transform and Z transform. So Z equals to R into e to the power j omega, because we are moving on to the frequency axis. So this is radius is equal to 1, and um, this axis, this circle, it is e to the power j omega, right? So if we perform if you get from here to here, what we get, x of z equals to uh, summation of n equals to minus infinity to infinity x of n z to the minus n, which is basically your xa. So we will be replacing this z over here. So we get this equation uh, because xz r into e to the power a. So if you see, it is basically the perform this rearrangement, you get f of x n multiplied by r to the power minus n. When r is equal to 1, x of e to the power j omega, it is equal to f of xn. That means, what does it mean? When you are moving on the unit circle, you are basically considering the Fourier transform. So with this, we finish the chapter. If you have any questions, we can discuss.